Here we show you TouchPass, an on-touch user authentication system designed for smartphones, leveraging active vibrations. This is a joint work with Shanghai Jiao Tong University and Rutgers University. Nowadays, smartphone becomes the most frequently used device for almost everyone. People use smartphones to send messages, check emails, watch videos, play games, shopping online, etc. In this environment, we touch our smartphone almost anytime, anywhere, and with various touching moods. Some of them are shown here. Therefore, the heavy usage of smartphones and the very frequent touching behaviors calls for an on-touch user authentication scheme that can apply for different touching moods. In other words, there is high demand for a behavior-irrelevant on-touch user authentication scheme. If we take a look at the roadmap of on-touch user authentication schemes, there are three basic directions: behavioral biometric-based user authentication, physical characters-based user authentication, and combined features-based user authentication. Most existing works are behavioral biometric-based, which uses the behavioral features of touching behavior. For example, touching position, touching time, touching force, to build an user authentication system. And more recently, there are works combining these behavioral biometrics and physical characters, such as the shape of touching hands, to build an user authentication system. But different from all these works, our work focusing only on the physical characters for user authentication. So, why we are using only physical characters? To answer the question, we first show that why we not use behavioral biometrics. There are two drawbacks of behavioral biometric-based user authentication in this case. First is intra-class variability. That is, a user could perform the touch behavior quite different in two separated operations. And second is their mimic attack vulnerability. That is, a spoofer could first observe how a legitimate user behaves and then mimic the exact way of touching operation. For experienced spoofers, they could do it very well, and the operation could be very similar to the user. Then let's combine with these two drawbacks together. We can see the dilemma here. The authentication either is too strict for users to parse, or too easy for the spoofer to break. So the behavioral biometric-based authentication system could hardly be accurate and reliable at the same time. And that is the main reason why we do not apply it for on-touch user authentication. Then we would like to show why we do not use mixed features, and that's mainly for the security reason. So let's consider a mixed authentication system with part of behavioral biometric and part of physical characters. Then in ideal case, for a legitimate user, he scores A for behavioral part and B for physical part. Then the total score S he got is larger than a predetermined threshold S subscript 0, so the authentication succeeds. While for a spoofer, he has his own behavior score A and physical score B, but the total score S is smaller than the threshold, so the authentication fails. Now we further make some more assumptions about the score, both physical score and behavior score. For a legitimate user, he could get score A between A subscript 0 and 1. The variance comes from the variability for different behaviors. and he could score B close to 1 because physical characters are usually stable. And for a spoofer, he could also get score A larger than A subscript 0 by mimicking the behavior of the legitimate user, and even better than the user at some times. But the score for B should be much smaller than 1 because it could not mimic the physical characters of the user. Then, under these assumptions, we could show that the larger part of behavioral biometrics, the authentication system, is less secure. Therefore, for security reasons, we would like to explore only physical characters for on-touch user authentication system. And that explains why we use physical characters. And the following question is, what characters can we leverage? Considering most operations on smartphones require finger touching, we would like to explore the physical characters of human fingers to identify different users. And everyone does have unique fingers, as they can be different in many ways, including geometry, bones, muscles, and even conductivity. And the last question is, how can we capture the physical characters? So to capture the physical characters of human fingers, we utilize active vibration signals that can be generated by smartphones. Typically, most smartphones could generate single-frequency vibration signals, and it can be divided into two states. The transient state, when the vibration signal starts and varies, and the steady state, when the vibration signal reaches a balance. So different states has different physical models. For transient state, the vibration signal first generated by the motor in smartphone and then transmitted to the connected part of user's finger and the smartphone screen, while parts of the signal transmitted to the finger and other parts are reflected back. Clearly, the physical characters of the finger could influence the process of this transmission and reflection, and this may show different patterns in the vibration signals. Here we show some basic results. The frequency analysis of vibration signals collected in transient state show that the frequency, amplitude, and distribution are different among different users. And then for steady state, the vibration signal comes to a balance. So in this case, the smartphone and the touching finger should be considered as a whole vibration body. Then the vibration system is a typical spring mass damper model under forced vibrations. And the physical characters of the fingers could directly affect the parameters of the model and make the vibration signal different among different users. From the basic experiments, we could see that although the main frequency components are close because of the vibration balance in steady state, but for minor frequency components, which we zoom in here, they could still embed the features of different users. Based on the study on vibration signals, we propose our system TouchPass, which has a register phase and a login phase. In register phase, after user touch, the system generates and collects designed vibration signals, and then extract features from the received signals. After that, a behavior irrelevant classifier is trained using the extracted features. Then in logging phase, the same signal processing and feature extraction process are conducted, and the classifier obtained from the Register phase is then used to classify the legitimate users and spoofers according to the features obtained in logging phase. First, we take a look at the signal processing part. We generate the vibration signal by turn on or turn off the vibration motor on smartphone. Here shows our control signal and the corresponding collected vibration signal. Specifically, we create a quick start for signal calibration and turn off the motor for 10 milliseconds, then turn on it for 90 milliseconds. Repeat the process for 3 times. This is to ensure both transient state and steady state of vibration signals are covered, and the whole vibration process lasts for only about 300 milliseconds, which can be served as a normal touch feedback to users. Then we further separate the received vibration signals into transient state and steady state, according to the frequency variance of received vibration signals. As we can see from the figure, A is related to the transient state, B part is related to the steady state, and there is an extra C part is the state when the vibration vanishes. After that, we enter the feature extraction part of the system. For transient state of vibration signals, since the vibration signal is highly dynamic in this state, we would like to capture the changes in signal amplitude and frequency as much as possible. So both frequency and time resolution need to be high. To achieve this goal, we apply a continuous wavelet transformation to the vibration signals to ensure both frequency and time resolution, and then collect the stripes in the time-frequency plot, as we can see in these two figures as the features. And then for steady state of vibration signals, since the differences among users are not very obvious, we would like to amplify the differences of minor frequency components and capture the dynamics of different frequency bands. Therefore, we apply substrom processing to the vibration signals. Substrom is the opposite of spectrum, and it can reflect the small dynamics in different frequency bands. The well-known MFCC used widely in voice processing is a special kind of substrom. And we can see here, after substrom process, the differences between two users become much more clear. Then, after that, we enter the classifier training part. The features we extracted from vibration signals contain both behavioral biometric and physical characters. They are mixed together, and we would like to remove the influence of behavioral biometrics as much as possible, leaving only physical characters. To do that, we first conduct a training sample selection process. In particular, we also collect the behavioral biometrics separately from the touching screen sensor of smartphones and use that data for training sample selection. If two samples belong to the same user, we only choose the samples with different behavioral biometrics as training samples. While if two samples are from different users, we only choose them when their samples are with similar behavioral biometrics. Then we have many selected training sample pairs. The goal is to let the classifier reduce the weight of behavioral biometric and increase the weight of physical characters. And we did that by using a special neural network model, Siamese network, as the classifier framework. As the name suggests, Simon's network always takes a pair of samples as input to train the parameters of the network. So the selected sample pairs could fully play the effect to reduce the influence of behavioral biometrics and put more weight on the influence of physical characters. And that's exactly what we need here. Also, since the system is designed for smartphones, we would like to make it lightweighted. Here we borrow the idea of knowledge destination to offload the training efforts to offline process by constructing a teacher-student network. Then the parameters trained by the teacher network with multiple users could help the training of student network for a specific user, so that it only requires a small amount of data and training effort from the specific user. At the end, we show the final user authentication step. For each user, the system uses the classifier to build a feature template into a template pool. If a user fits one of the templates in the pool, then the authentication succeeds. If none of the templates in the pool is activated, then the authentication fails. To evaluate our system, we use 3 different types of smartphones as shown here, and totally 75 volunteers are recruited. They are further divided into 3 groups, each with 25 volunteers, to conduct experiments in 3 different environments respectively. The environments are lab, bar, and bars, with different level of vibration noises. To better evaluate our system, we built 3 versions of our system. The original TouchPass model used physical characters for user authentication. The behavioral TouchPass model used behavioral biometrics for user authentication. And a mixed TouchPass model used both the physical characters and behavioral metrics. And we have our volunteers play the roles of both legitimate users and also spoofers. Here we show the overall authentication results in 3 different environments. The accuracy are good for all environments, and the lab environment has the best performance, while the BOSS environment has some accuracy degrades because of external vibrations. And for the 3 models, it can be seen that the original TouchPass outperforms behavior relevant versions in all 3 environments. To be more specific, if the behavior of registration are very close to the login touch, then the mixed TouchPass actually could have the best performance. But this is a very strict case. And for most cases, when the login touch is not very similar to the registration one, the original TouchPass does have the best performance among the 3. We further show the performance of the system under 2 typical attacks, mimic and replay attack. It can be seen that our system could make the false positive rate under 2% for both attacks in all 3 environments. So to summarize, we show that active vibration signals can capture physical characters of human fingers, and further design a behavior irrelevant on-touch user authentication system leveraging built-in sensors on off-the-shelf smartphones. And we also demonstrate the security and variability of behavior irrelevant user authentication scheme in different realistic environments. And that's all for the video. Thank you for watching. Hope to see you again in MobiCom 2020.